Morning, everyone. Hope you all had a relaxing weekend. Welcome back. Today we're going to start where we left off on Friday and talk about an application of the stack ADT, and that's bracket matching. It's probably not something that you think about in day-to-day life, but it's something that comes up all the time in code editors, especially, and also calculators. When you're compiling your code or running it at all, there's going to be some sort of bracket matching algorithm running to make sure that the code you're writing actually makes sense. And it turns out a very, I don't want to say easy, but very applicable way to do this is to use a stack. So you're given a string. You could imagine it being the source code for some file, and you're writing a code editor or a compiler. You're given a string, and you're processing it character by character. Each character is either a digit, an operator, or a bracket. You can generalize this for a code editor to say that each character is a bracket or not a bracket. We have specific left brackets and right brackets. Our algorithm to match brackets is to go character by character, and then whenever you see a left bracket, add it to the stack. And then that's all we have for now. We have pseudocode for it here, but rather than go through the code, I'll just do an example. I'll do part of that first example. So you can probably eyeball this. This string is bracket matched. For each left bracket, there is a corresponding right bracket. Of course, there's no eyeballing it when you're writing code. So we'll run our algorithm roughly to see that this string is indeed bracket matched. So I'm going to have my stack here. I'm going to draw it really big so that it's hopefully not too ambiguous with the square bracket that I'm about to add. We get this square bracket and add it to the stack because we go character by character. We see 3, that's a number, so we ignore it. Times, asterisk, whatever you want to call it, that's an operator, so we ignore it. Square bracket, left square bracket, in fact, so we add it to the stack. Left curved bracket, think parenthesis. I don't actually know what they're called, but you know it when you see it. I'm going to add that to the stack. 6 is a number. Slash for division is an operator. 2 is a number. And then this is the moment where it's like the stack's time to shine. When we detect a right bracket, we're going to pop it from the stack. Remember, stacks are first in, first out, or last in, first out. In any case, the most recent thing to be added to the stack is the first thing to be removed from the stack. Plus, that's an operator. 5, that's a number. Closing square bracket. We pop that. And then we're at the end, and we see that the stack is empty. This, it turns out, is a guarantee that the string is bracket matched. Now let's do another example with a string that is bad, not bracket matched. This is totally something that you might write. Well, probably not with all these constants, but it should be a very familiar situation when writing code with lots of nested operations. So we're going to verify whether or not this is bracket matched. That's a number, that's an operator. Ooh, that's a bracket. I see another bracket. Then 7, that's a number, plus, that's an operator, square bracket. Number, operator, number, right square bracket, so we pop a bracket off the stack. Left parenthesis, we pop that off the stack. And then we end the algorithm seeing that there's still something on the stack, so it fails. This string is not bracket matched. And then I'm going to change this example a tiny bit to attempt to bracket match this. Let's say I added a curly bracket to the end. So technically, every left bracket has a corresponding right bracket. But part of the algorithm, and this is kind of straying away from the purpose of using a stack, but it's important for bracket matching. The brackets are not considered matched because they're not of the same type. So if we go through it, we would push those two round brackets, push a square bracket, pop that, and then when we get to the curly bracket, we don't pop anything. Instead, the whole time we've actually been using the peek operation before popping to verify that the closing bracket is the same as that opening bracket. So if we peek and see a bracket that isn't the same as what we originally pushed onto the stack, like it's not corresponding to the bracket we pushed onto the stack, then it fails. And this is the pseudocode for what we just did. You go character by character. If the character is a left bracket, we push it. If it's a right bracket, we check, is it empty? And if we peek at the top of the stack, does that bracket match the thing that, or the character we're seeing right now? If so, pop it and move on. If not, say answer false, which will eventually make us return false. Once we've gotten to the end of the stack, we check, is it empty? If it is not empty, then we get answer equals false, so the algorithm returns false. This is sort of a useful practice exercise for ADTs, specifically stacks. You could think about how you would implement the stack ADT using an array, and then just write the code yourself. And then also use big O notation to analyze the time complexity of each of the functions that you write. And if and when you're doing this yourself, I recommend trying it out both formally and informally. Try it formally by actually going line by line, creating a cost function, and then using the definition of big O to prove that your cost function is in big O of, in this case, it's probably going to be either 1 or n, but whatever you think it's in big O of. And then try it informally. Try it the way they do it in the real world. Just sort of eyeball the code. Go like, that's a loop. It's probably O of n. And if your informal answers are the same as your formal answers, then you know that you're getting it. We're going to go into slightly more detail about a linked list implementation of a stack, though. Because there isn't really more than one way to do an array. But as we saw earlier, there are many ways to do a stack, or many ways to do a linked list. Should it be sorted or unsorted? Should it use dummy nodes? Should it be circular? How should it be linked? Turns out we can keep it simple for the sake of a stack. The extensions to the basic linked list were basically done because of searching or iterating. We wanted to be able to search through the linked list quickly, or occasionally iterate forwards and or backwards through the list. But since the stack operations always operate on the top of the stack, you're never going to search or iterate through a stack. The basic linked list is fine. Unsorted, linear, singly linked, and with no dummy nodes. Here's another exercise you can do. Though I think it's actually, it's actually on the slide, so I'll go through the solutions. All of the stack operations are pretty easy to do in a linked list implementation. And if you're trying it yourself, which I recommend, even though we're going to go over the solution pretty much immediately, you can try it yourself on your own after the lecture. You can assume that the stack isn't empty. So to push, we just add a node to the top. To pop, I'm going to go over top first. This top operation, I'm used to calling it peek, but the words both mean the same thing. We just check the top of the linked list and return whatever data it contains. Pop is more intensive than top. You get the data from the top node and then delete that node from the linked list. And take a moment to be grateful that you're doing this in, I want to say Java, but in this case, just pseudocode. And that you're not doing it in C, so you don't need to worry about freeing any memory or whatever. And another part of the exercise is how you would impose a maximum size on the stack. To do this, I would keep track of the number of items that are currently in the stack. So my stack class in code would contain a linked list and an int representing how many items are in the stack, and another int with the maximum size. When you push, you increment the number of items. When you pop, you decrement the number of items. And during a push, you compare the number of items in the stack to the maximum and refuse to push if is already equal to the maximum. This is also explained in the slides. And it's worth noting that all of these operations have O of 1 time complexity. If you did this the formal way, you would look at each line and see that it only contains primitive operations, get a cost function that is a constant, and then either use a definition or use that one fact about how any constant multiple of a function is in big theta of that function. And then anything in big theta of a function is in big O of that same function. Bada bing, bada boom, it's an O of n. But as I keep saying, the way you'll do it after you finish this course, and probably a couple more theoretical courses in your degree, is that you'll just look at the code, notice that there are no loops, and there are definitely no evil jumps like gotos, and there are also no function calls. See that and say, oh, it's O of 1. So that's all we're going to say about stacks. Now we're going to move on to the other data structure that we went over at the end of last week, the queue. A queue is very similar to a stack, except when you remove an item from a queue, instead of removing the most recently added item, you remove the least recently added item. I'll go through the operations soon, but I'm going to skip ahead to notation. We have these sort of special angle brackets that we use for the queue. I said special, but they're not really special other than the fact that they point in the same direction. The direction they point to is towards the front of the queue. So you could imagine a bunch of people standing in line for something, and the thing they're standing in line for is to the left. If you add a new entry, it appears at the back of the queue, so at the right. And then when you dequeue an item, it's removed from the front, which in our notation is the left. The notation, like the direction that the notation goes in, is kind of arbitrary. This is just the convention of the course that we use in this course, but there's no like objectively correct cosmic reason why we enqueue to the right and dequeue from the left. But I think this works nicely with our stack notation in that as you add things to the stack or the queue, it always moves left to right if you keep adding stuff, which is the way that we write in English, so it's convenient. So I'm going to copy this example while going through the operations. Enqueue adds a new entry to the back of the queue, and dequeue removes an entry. We sort of already just went over this, but I suppose it's helpful to do them in the drawn example. So to enqueue, I'm going to put number 6 in there. I had to redraw the right bracket, but if you don't feel like doing that, it's totally valid to just write the bracket far away, and then I'll understand that This is still a queue with 6 at the back and 8 at the front. You'll end up with some kind of ugly white space, but you won't have to erase stuff as often, so I think it's a win overall. Of course, when you're doing your assignment, you should probably write it more tightly, but this little trick is good for rough work. DQ removes the entry from the front of the queue and returns it. So in this case, we would remove and return the number 8. Front returns the front entry, but does not remove it. It's analogous to the top or peak operation in a stack. So that would return 2, but not modify the queue. Is empty. Uh-oh. Checks if the queue is empty and returns a Boolean. In this case, the queue has stuff in it, so it's not empty. Return false. The constructor creates a new empty queue, and is full can be used if there's a size limit. This is an implementation detail, not really part of the ADT, but just like with stacks, and as you might already predict, there would usually need to be a size limit for arrays, but not for linked lists. The implementation of a queue is a bit more complicated than that with a stack, especially if you're using an array. But we'll look at the linked list implementation first. For a queue, we need 2 pointers to the head and the tail of the list. And as of right now, we're not sure which is which. Like, which one's going to be the front of the list and which one's going to be the back of the list. This actually doesn't really matter if you're using a doubly linked list, but for a singly linked list, we're going to choose which of the head and the tail is the front and the back based on whether it's possible to, or what it's possible to do in constant time. At the front of the queue, like where elements get removed, we're going to want to delete in constant time. And at the back of the list, where elements are added or in-queued, we'll want to be able to add in constant time. So I'm going to guess wrong. Let's say the head is the back and the tail is the front. Don't write this down because it's wrong. I peeked at the slide that's coming up next so that I can demonstrate why we don't do it this way. So if we want to add a node to the back, that's simple enough. So we're in-queuing an item right now. We would move the head's pointer to our new node and then make it point to our former head. So far, so good. But now, what if we want to delete an item from the front? Say we want to dequeue a node. Well, as you know, to delete a node from a linked list, you make the item behind it point to the thing in front of it, thus leaving the middle totally isolated and eventually to be garbage collected. So how do you get the second item in the queue? In this case, it's completely impossible to get to from the front. Like, there is no arrow that points from tail to this node. So we'd have to start from the head or the back and then do a linear search. Is this the last node? That is, does the link equal null? No, 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 yes. So this is the last node. Then we would have been keeping track of the previous node, find it here, and then we'd finally turn this into a null pointer, and then also change this pointer to go to the second node in the list. The important part here is that this took linear time. The larger the linked list is, the more steps this will take, because it had to go through every node in the list in order to get to the node that it had to change in order to delete from the front of the list. That's bad. We can do better. I'm not sure if I should erase this or not, because it has potential to be misleading to anyone looking at the annotated slides. Yeah, I'm going to nuke it. The way we should do it, the way we actually do it, is to make the head of the list the front of the queue and the tail of the list the back of the queue. This lets us do all the operations we need in constant time. I'll do a demonstration of that too. So I think first we did adding a node to the back of the queue. So we create a new node. We have access to the node at the back of the queue. So we make it point to our new node and then modify our existing back pointer to point to our new node. Simple. And then removing or dequeuing a node from the front is the thing that gave us issues last time, the thing that we couldn't do in constant time. But now it's easy again. We have access to the thing that the front of the list is linked to. So we just make it point there. And not point at the former front. The garbage collector will eventually notice that nothing references this node and destroy it. There's another way we could solve that conundrum of where do we put the front and the back of the queue in a linked list? And that's to only store a pointer to the back of the list, and then just make the linked list circular. So to I'm confusing myself here. Yeah, to add a node to the back, you would make the former back link to it, make it link to the second node, and then redirect the back pointer. How do you remove from the front? I'll have to take a moment to figure this out. I think it's a matter of deleting this node. Whatever, I'm not going to worry about this right now. It'll probably become clear to me right after I stop presenting and become clear to you immediately. But everyone knows you'll lose like half your brain cells when presenting. Now, the linked list implementation of a queue was a little weird. The array implementation of a queue is very weird. So, as with the stack, you suppose you have an integer array, and it has a length max size, and you want to write the function enqueue, dequeue, front, is empty, and is full. So let's say we have an array Can I move this? There we go. Okay, you have an array and you want to turn it into a queue. So a sensible initial design decision might be to add items to the queue from the left. So let's say we want to enqueue the numbers 1, 2, 3, 4. You might add them like that. And then to keep track of the front and the back of the queue, you might just keep track of a couple indices. Or actually, the front of the queue is obviously index 0, right? So the back of the queue is just the number of items that are in it so far, -1 because of 0 indexing. I'm going to label this as B for back. And then when you dequeue an item, you remove it from the array. And like in your implementation, you'd have some sort of value representing empty, maybe like 0, -1, null, whatever makes sense for your application. In this case, we're just going to have empty squares in our array. So you remove it from the front, and then I guess you have to decide how to handle this. You could move all the array elements to the front. But notice that I had to do that erase and rewrite for every member of the queue. Whereas with the linked list, I only had to do one operation. Imagine if this queue had 100,000 things in it. With a linked list, I would just do those 2 arrow redraws. With the array, I'd be here all class. So that's kind of unacceptable. Another thing we could do would be to just keep another index. Oops. I'm going to call this F for front. So now the actual contents of the queue can be anywhere in the queue. And we keep track of exactly where using these front and back pointers. I'm going to keep in-queuing and de-queuing stuff from the queue, and we're soon going to run into another problem. So I just in-queued a bunch of stuff, and I'm going to de-queue a few items. So now I've arrived at the end of the queue. If I were to in-queue an item, what should happen? You could say that since we've arrived at the end of the array, it's full. But like, what if you've de-queued a bunch of items already? Is this a full queue? Yes.
Why don't you just make a circular array?
Woohoo. Let me keep talking for like 30 more seconds. Is this a full queue? Shouldn't be. So, something you could do to get around this is to modify whatever algorithm you are using to set the back pointer to say that like b equals b plus 1 mod array size. Which will cause, as I think you were already onto, the index to wrap around. So now the back pointer goes before the front pointer, but that's fine because we have the modulo operation. And then it just works. The only, or the last sort of gotcha that you might encounter is that it may be difficult to tell when the queue is empty or full because now that the back can be either before or after the front, you can no longer use some sort of condition like the array is not empty if back is strictly greater than front or something like that. I think that to address those last 2 points, you would keep track of the number of items in the queue and compare that to your array size. And then it's full if the number of items equals the array size. And it's empty if the number of items is 0. Just like the stack, actually. Yeah?
Why don't you just check when you go to add another item? Or even if you look, if you like b plus 1, you need that same thing. You can check with the filter, right? Or your possibility column. If they're the same, well then obviously it's full.
Wait, could
Keep track of the extra variables. If you put something, what is that? Oh, 1 is good.
could you repeat that? I couldn't hear you over the door.
So if the fill point of your f is equal to your b, right? If you're trying to increase your b by 1, right? And they're the same, then it's going to be full. So you don't have to keep track of other stuff.
Okay.
That'd be one function. Is it full? And then you just basically where you have b equals b plus 1, you just check if f is equal to b plus 1 mod your array size.
So if f is equal to b plus 1 mod array size, then it's full? Is that what you're saying?
I think that's what it's saying.
I think it is too, because you're right. that is that would work for keeping track of whether it's full. And then if it's empty, then B would be equal to F. And then you can check that to check emptiness. So yeah, I think that's actually better than the solution I suggested. Both of ours would be constant time, but yours would use slightly less memory. Yeah?
Would the F also encounter a situation where it would need to go through the modulo array size if we were being pushed like from the back to the front?
Yeah, definitely. If I dequeued these two, then exactly, F would appear at the front again, and it would use a incrementation algorithm very similar to what we did with B. So this may or may not show up as an assignment. I recommend trying it yourself if you have the time anyway. And like, speaking of things that could show up in evaluations, I forgot to mention earlier that analogous to how something with a stack, right, I mentioned on Friday that this is very likely to be a quiz question eventually. Get a list of operations on a stack and note the return value and draw the stack after. I am just as likely to make a quiz question that asks you to do this, but with a queue. Might even be the same sequence of operations. All right, I'm going to start an example that we'll go deeper into next class. This is like bracket matching, but the sequel, the hard mode. And it's arithmetic expression parsing. Kind of learning how to make a calculator. The order of operations in arithmetic is, well, the thing you learned in grade school. You might see or you might have seen, I don't know, a meme on Facebook or whatever that goes like, ooh, 99% of people can't solve this. And it's an arithmetic expression where the order of operations is ambiguous. You get 6 plus 3 times 2. Some people in the comments are going to say that it's 6 plus 3 equals 9, times 2 is 18. And then they're going to get into a very intense argument with the people who know the order of operations and say that this expression is 3 times 2 equals 6, plus 6 equals 12. And then Facebook's going to get this sweet, sweet engagement and ad revenue either way. So with this order of operations, writing an algorithm to parse an expression like this and solve it would probably be really messy. You could imagine your code parsing the string to find high priority operations like brackets, exponents. Ooh, that's multiplication. So we solve that, go through the string again to find the next highest priority operation. In this case, it would be addition, so you solve that, and then get the final answer. This is another opportunity, actually, to talk about intuition with big O notation. That crappy algorithm I just thought of to go through an arithmetic expression written the normal way and solve it, it would have to go through the string once for every operator in the equation. And whenever you have a situation where an algorithm has to parse the input for every item in the input, that does a number of operations, something along the lines of n times n, go through n inputs n times. So that gives us a time complexity or a cost function that would have an n squared in it, hence big O of n squared. We're going to make a arithmetic expression parser that's able to do its thing in linear time. It'll only have to parse the input once. And if you were hoping for some really clever way to parse an expression like this, you're going to be disappointed temporarily, because we're going to use different notation for our expressions. And then, not sure if this is actually in the slides, but there is a way to quickly convert from the familiar human way to one of the two slick computer ways to do it. The intuitive human way I mentioned, probably the only one you've ever seen before today, we call that infix notation because it has the operation inside or in between the two numbers. 3 times 2 as 3 asterisk 2 would be infix notation. Prefix notation puts the operator before the numbers, or before the operands. So 3 times 2, you would write as asterisk 3, 2. This generalizes to things that have more operations in them. 6 plus the result of 3 times 2 is written as plus 6 asterisk 3, 2. We're only going to be working with single-digit numbers in these examples, but you can imagine writing an algorithm for this that just stores a list of ints or something, in which case you could have multi-digit numbers just fine. And last thing I'll show is postfix notation. Number operation. We can see that we have some examples of infix notation expressions being converted to postfix notation expressions. And notice how the operators always come after the numbers. What we're going to talk about next class is how it turns out prefix and postfix notation can be used with stacks and queues to make a pretty convenient algorithm for parsing these expressions. All right, that's all. Have a good day.